Yep. So, hi everyone. Thanks for coming. My name is Georgi Todorovic. This is Nikola Prica. We are coming from RTRK company from Serbia. So we have been working as a team on various projects in field of compilers, debuggers, profilers, and so on. We are going to be talking today how far can we go with debug info in optimized code in LLVM, especially with an improvement by looking at function parameters, entry values at call point, at call site point. So since we know that debugging optimized code is very challenging even these days, we work very hard in order to improve that. So yeah. So RTRK is a software company specialized in system software and embedded systems. So as I said, we are part of the group working on compilers and tools from open source area such as GCC, binutils, LLVM, LuaJIT, and so on. So the group has been working on LLVM since 2010, and we are working on debug related issues in LLVM for the last 2 years. So yeah. Here are points we're going to talk about today. Firstly, we will start with some general story about debugging software release products. So also we'll describe a technique that can be used within debugger for finding some actual values of function parameters even they are described as optimized out. So after that we will point to some parts of our implementation in LLVM we took to support this feature, and at the end we'll show you some numbers that actually confirm that we are improving something in debug location coverage. So yeah, let's start. So software release products are compiled with some kind of optimizations. So for compilers like GCC and LLVM Clang, it is usually O2 or O3 level. So such a product might produce a core dump file on an embedded system, and it could be starting point of our analysis of the problem. So first thing we usually do after loading a core file into debugger on our local machines is analysis of the call trace from the crash. So through the optimization pipeline, we lose a lot of debug information. So in those call traces, we see a lot of optimize out parameters values. So actually, we also notice in those debug sessions that even if a variable is alive at some point, it could be clobbered even earlier and reported as optimized out. So yeah. So developers with more experience with debuggers are aware that some of those values could be found at parent's frame or frame above. So yeah, looking at this example here, we see that parameter X is reported as optimize out, but if we jump into frame 2, we are able to print the actual value at call site point. So yeah, if we can do that, why not optimize all this process within debugger? But in order to do that, we need additional information by compiler side. So in this example here, we see all that process optimized on both sides, debugger and compiler. And we also see these entry values printed out. So actually those optimized out values turned into actual values. So yeah. A little bit of motivation here to listen to the rest of the presentation carefully. By implementing this feature in LLVM Clang, we noticed that the number of fully covered function parameters increase even up to 15%, which is a very good number. So, yeah. There are several dwarf symbols introduced in order to support the feature. So, does everyone know dwarf? I hope no, yeah. For those who are not familiar, actually dwarf is standard for describing debug information on Unix-like operating systems. So compilers generate that, so debuggers consume it. So yeah. To mention that it was initially introduced by Jakub Jelinek, and it was implemented in GCC and GDB since 2011. So basically, those two tags represents call site and call site parameters. So those attributes describe them. So there is also dwarf operand that can be used within dwarf expression for describing actual value for parameters. So let's jump into real example. So we see here a real call site printed into debug info section. So it says that it lives at this address in memory, this called PC. Actually, it is address of a call instruction in memory. This call origin actually represents a reference to debug information about called function. This call site parameter is a child of this particular call site, and it says that it lives at register 5, and at call point it had value 7. So yeah, it's another example. So if the parameter has untouched, unchanged value through the course of the function, we can use this op entry value, actually entry value, for describing actual value for that parameter at the places where it has no location information at all. So let's imagine that a parameter has its scope from address X to address Z. But from X to epsilon address, it has location information. But for the rest of its scope, we generate additional op entry value for describing the rest of the scope. So yeah. So Nicola will continue with implementation details.
So hello everyone. I will present you entities that we introduce on IR and machine IR level in order to follow information about call site to the compilation process. I will also introduce you with some of the concerns that we have about our certain parts of implementation. So how many of you is familiar with debug info metadata in LLVM? So basically, I will explain it briefly. Basically, it is inspired by dwarf tags, and it is used to represent source entities such as file, functions, lines, lexical blocks, variables, etc. So since debug info metadata is inspired by dwarf, and we have that resemblance, and George showed that call site information in dwarf is represented by tags, tag call site and tag call site parameter, we decided to introduce di call site and di call site param metadata. So here we can see for call instruction that it has attached metadata node call site, which reference to call site metadata. And we can see that call site has following arguments such as scope, file, it has reference to array of di call site param, it has line, and it has reference to called subprogram. And for the call site param, it has argument number, it has reference to variable metadata, and it has an expression over that variable. Now, if called argument is constant, here we would have only the expression which represent constant. So this DI call site param is used as a backup location for catching this parameter at entry. I will show primary location later. And with this metadata, we actually emulate jumping back into functions frame and printing certain expression. We also need to mention that in order to use this new value, entry value, for representing other variables, especially parameter variables, we need to verify that that parameter has never been modified through the course of the function. So in order to check this, we used SEMA constant check, and we wrote that information inside parameter variable debug metadata. So this approach has certain benefits and it has certain limitations. And regarding benefits, it resembles to dwarf tag, and it follows that idea. Also, we have additional backup for representing of call site parameter once primary location is lost. And also, we are able to produce tag call site parameter that can have DVOP entry value in itself. And that means that we can look 2 or more frames up in search for some entry value. And regarding limitations, there is no support for representing expression between multiple variables. To do so, we would probably need new kind of debug metadata. Also, since we are emulating jumping back and printing variable location, we are able to do so because there is a system for tracking variables location in LLVM, but there is no support for tracking functions return value location. And that is the reason that we can represent arguments that are functions, function calls. Also, there is no easy way to represent address of variable. It is hard to distinguish in debug metadata between variables address and variables value. It is not impossible, but it is pretty complicated. Also, we need, in order to provide reference in DI call site parameter to DI variables metadata, we needed to change a pretty standard and stable interface of DI builder interface. And we previously creation and preservation of variables metadata was done in one function call, but we needed to separate this. Next pass that I'm going to talk about is instruction selection pass. Now, it is important to mention this pass since this is the place of our implementation that could possibly be improved. So we implemented general algorithm that should work for various architectures. Job of this algorithm is to recognize instructions, copy instructions that forward function arguments to the following function call. So we can see, for example, this pseudo instructions like this. Process of this algorithm starts after call lowering, target call lowering, whose result is target call lowering info object. And this object in itself contains a sequence of selection DAG nodes that represent call sequence. So we iterate through this sequence and we search for copy to reg selection DAG nodes. These nodes should later be mapped to copy instructions. And then we try to match copied value with one of the function's input argument. Such verification is required because we could have additional copy instructions inside this calling sequence. For example, for variadic functions, additional register copy instruction is required. And some of the function calling ABIs might load additional value that is not function argument. This algorithm could be lowered to target specific level, more precisely to the level where call sequence is being generated. So once we have matched these nodes, we just preserve them in instruction selection representation of call site, and later we emit them as dbg call site and dbg call site parent pseudo instructions. So our backup implementation pretty much relies on how dbg value pseudo instruction is handled. This pseudo instruction is used to track variables location in registers, virtual or physical stack locations, or some address, or in some addresses. So here we can see this dbg call site and dbg call site parent instructions. For dbg call site, first operand is Boolean value whether reference call is stale or not, and the second argument is provided if call is indirect call, and then it is that call's register location, and last argument is reference to the AI call site. Now this could be implemented differently, but we choose to keep all information about call site at one place. Now we can see here the dbg call site param instructions are attached as a bundle to dbg call site. And the first argument of dbg call site param is a register that forwards argument to the following function call. Second is reference to di call site param. And the last arguments represent the location that is loaded into parameter forwarding register. Now I will mention that this machine IR is produced with LLVM 4.0, and I have just stripped some of the instructions in order to code to be more clear. And here we can follow behavior of variable c, and we can see that it is indeed forwarded as the first argument of function foo. So first value, its first value is value 4. After this function call, it is returned as EAX and moved to EBX register, and later it is forwarded as a function call argument through EDI. So in order to handle this instruction in backend, we needed modification in a prolog, epilogue, insetter pass, register allocation, split kit, virtual register writer, and most important for us in light debug values pass. Now, a job of this pass is to broadcast dbg value pseudo instructions into successive blocks where preserved location is not clobbered, where that location is valid. So as a natural, it should emit replacement for parameters for dbg values that represent parameters. And once these locations are clobbered, we should emit this dbg value with new expression, dvop entry value. Also, this pass knows for each basic block range which variables are live at that point. So also we adjust dbg call site param instructions here. And by adjusting, we mean that we delete these instructions that are not valid. Instructions that are not valid are ones that do not have primary location nor backup location. By backup location, we mean invalid backup location are ones that reference variables that are not seen at that point of block. Also, regarding producing this, printing this location in object file, it is done in dwarf debug pass, and it is handled similarly as for dbg value instruction. So there is nothing special to say here. It relies pretty much on similar structures as dbg value. So Georgia will now present you some measurements that we have.
So yeah, we'll show you some numbers that actually confirm our improvement. So in order to do that, we used a logstat tool from elf-utils package. It actually looks for a scope of a variable and calculates a debug location coverage we need. So for testing purpose, for these slides, we used GDB 7.11 and spec 2006 benchmark. So also we noticed increment in debug location coverage. Also, we didn't touch code generation, which is very important. There is no change in text, BSS, or data sections. There is only change in .debug sections as expected. So yeah, and just to mention that for O2 and O3 level, we noticed very similar results. So yeah, first example is GDB 7.11. So we built the latest release version of that. So we noticed over there the increment of fully covered function parameters for about 15%, which is about 17,000 more debug variables with fully debug location coverage, which is a very good number. Yeah. So average coverage per variable is increased for about 10%. So there is no change in code generation. There is only change in .debug sections. And in this case, we noticed build time increase for about 2%. So yeah. Another example, yeah, we built spec 2006 benchmark. It is a huge project designed to stress processor, CPU, compiler, memory subsystem, and so on. It is pretty standard test suite. So over there we notice the increment of fully covered function parameters for about 8%, which is about 12,000 more debug variables with fully coverage. So in this case we noticed the increment of average coverage per variable for about 4%. So there is no change in code generation. The change, as expected, is only in .debug sections, and build time in this case increased for about 1%. So yeah, those improvement in debug location coverage is most important.
So I will just wrap up this presentation. So after we finished this implementation, we identified two main spots in our implementation that require further discussion. So there is a question about usefulness of DI call site param, and there is a question whether algorithm in instruction selection phase should be lowered to target specific level. But that requires target-specific knowledge. And what does our implementation provide? It provides, most importantly, correct debug data. We tried to be strict as much as we could in order to achieve this. Also, our measurements showed that we didn't touch code generation process, and this is important because our implementations takes part through the whole compilation pipeline. So It is also important to mention that it provides infrastructure for collecting information about call sites. We believe that we have touched all necessary passes and that current flow is sufficient, but it certainly needs some improvements. It gives us desired results. It gives us improvement in parameter location coverage, and it provides us new functionality in debugger. It provides us function entry values. And these entry values in debugger clearly provide better user debugging experience in programs produced with LLVM. So, and before we finish, we would like to mention that we have implemented this feature in collaboration with Cisco, especially with Anand Sovda and Ivan Baja. So thank you for listening, and thank you for your time.
I was curious in the slide where you showed the measurements.
Yep.
So you show -G-F emit param entry values.
Yeah.
Is that -F flag added into the -G groups or any of the G level groups, or is it something I explicitly need to enable?
Actually, firstly, just to mention that so the question was, does we include this F emit param option into -G default options? So actually, for now, no. Why? We initially implemented this for an internal version of LLVM 4.0 compiler, and we tested this within Cisco on large projects. But and also we introduced a new option in order to make all of those testing and make sure that we didn't clobber anything, especially code generation. And as soon as we make sure that everything goes well, we will include this in default -G. And actually, just to mention that we are in the process of backporting this onto LLVM Trank, latest version. Actually, we backported it, so we are finishing testing phase. And as soon as we are done with that, we will post those patches onto LLVM. So
Awesome.
yeah,
Anything we can do to
yeah.
debug info is a major help.
Yeah, thank you. It's supposed to be this month, so yeah, we expect this. So
I noticed you had some target-specific code in there. Is it your intention that you targets implement this yourself, or are you going to implement this for all backends?
So the question is, where is the target-specific implementation? Target-specific implementation part is in instruction selection, and it is part for selection DAG nodes generation. It concerns about how some targets generate this call sequence. And we noticed that there are some issues for matching those selection DAG nodes. Because you could, for example, you could have some node and you could have node value, and you could have that node value wrapped up with some extension, for example, zero extension or sign extension, and you can't match these two nodes. You just need explicitly to match this selection DAG node, which does not have this extension. Also, we also implemented some salvaging function that preserves some location where we, for example, when we lose track of primary location in virtual registry writer, we go back up to InStream to search for instruction that loads that parameter. And we try to interpret that instruction. We implemented this salvaging for x86 LIA instruction, for example.
But when in the upstreaming process, are you going to implement that for all targets, or is it selectively people turn this on and they'll have to make sure the backend supports
Sorry, could you repeat the
Yeah,
question?
so when in the process of upstreaming, as it stands now, it sounds like some parts will only work on x86. So I'm just thinking, are you going to try and approach the other back-end implementers to get them to implement it, or are you going to implement it yourself?
No, yeah. So the question is whether this only works for 86 architecture. We just tested it for x86 architecture. We tested this feature only to build complex software for various architectures such as MIPS and ARM. But we didn't go into deep details to see where we lose information. So.
You have the measurements comparing the coverage that GCC provided in the same contract?
Actually, yeah, when we started looking at this feature, and yeah, we did, yeah, we had, seen those measurements. We calculated those numbers also with GCC, but comparing GCC and LLVM doesn't make sense because the code is different, generated code is different. But yeah, honestly, LLVM is still behind GCC in debug location coverage because, yeah, this feature is pretty standard over there since 2011, yeah, and it was improved in stages. So yeah, if your question was does GCC has better debug location coverage, yeah, it has, but LLVM with this will have certainly better location coverage, yeah, and we are running to even be at least like GCC,
You can use that as a benchmark. There's still some room for improvement.
yeah, yeah.
I had a related question to that.
So yep.
Okay, so first of all, thank you very much. This is really useful work because it's an area where LLVM, debug for optimized code in LLVM is behind GCC and has been improved. Have you looked at the impact of this actually on the GDB regression test suite? Because that actually has some quite good corner cases for testing things.
So the question was whether we looked at GDB for some corner test cases. Thank you for that question. We didn't, and we will gladly look at. We will investigate that. Thank you.
So just to mention here that LDB doesn't support reading of entry values. I think that for now it will be just ignored. So, but within GDB we tried debug user experience even with binaries compiled with LLVM with this version, and yeah, it works for a bunch of cases. So thank you for the question. Yes?
You may have mentioned it, may have missed it, but is this functionality only available when you're generating var 5, or is it also for var 4?
Actually, the question was if this functionality is available only for var 5. Actually, initially, it was introduced as a GNU extension and used in GCC like that. But since var 5 released, it is in this part of the standard. So for now, yeah, for this purpose, we internally generated GNU extensions as well. But yeah, it's supposed to be both of that, GNU and. Sure, yeah. We should support GNU as well as var 5 symbols. So yeah, thank you for the question.
So on these metrics, I'm not entirely sure exactly what the metric average coverage per variable really means, but I'm assuming that it's impossible to get 100% because some variables will be completely eliminated. There's no way to, even if you were perfect to find it. Do you know what the theoretical upper maximum number would be that you could strive for?
So the question is what is the theoretical maximum for coverage percentage. We use this tool logstat. Now it is not able to measure its variable visibility from where it is defined to last use of that variable. It is measure. It can only measure its coverage only to that lexical block where it is defined. So these numbers just show us how much we did improve. Show that we just improved something, and we similar. This tool was also used by Jelinek in his paper to show up this improvement.
Yeah, actually, it would be perfect if we have a tool that actually looks for a life of a variable. But yeah, we don't have that. We use just this one as a reference to measure improvement. Yeah, yeah. But if someone knows for some tool that looks for a variable's life, yeah, please feel free to advise us.
If there are no more questions, then thank the speakers.
Thank you.